So good afternoon. This is the overview of the lecture of today's lecture. Today we will introduce a novelty with respect to the context we saw up to now, so far. The vector space model. We gave a rough idea of the vector space model maybe during the first or second lesson, but the assumption so far is that we have documents and we can make queries on those documents according to the Boolean model, okay? So in the Boolean model, the idea is that all the documents that match a given query will be provided as a result, okay? So there is no ranking among the documents. All the documents that match a given query are provided as a result. The novelty here is that we introduce the concept of ranking the results, and this ranking of the results will be based on a new model that is not anymore simply the Boolean one, but in which we have documents that are vectors and queries that are vectors in a given space. Okay? This is the idea of today's class. Okay, good. So let's recap very quickly what we said last time. Okay, so the first thing is, what is the relationship that exists between the number of tokens and the vocabulary size? And so we saw that we have a pretty good approximation. Then we also saw that there is a kind of message in this picture that basically the frequency of the terms is described by this logarithmic curve, okay? There are very frequent terms. Let's give me an example about very frequent terms. The stop words in general, right, are very frequent, and there are very rare terms, okay? Then we start discussing, okay, look, but the concept of dictionary is pretty clear. The concept of Boolean query is pretty clear, but now we have also a matter of efficiency. So how can we compress both the dictionary and the posting list? And so we say, okay, we can compress the dictionary looking at the dictionary as a string with pointers, okay? And we can compress the posting list, not simply listing all the documents ID, rather listing the gap between the documents ID. Okay? And this allows us to get significant saving. And in order to store this saving, we saw a number of techniques to represent those gaps. We saw a number of techniques. One of those is the variable byte. The other one is the gamma code. And indeed, if you apply those techniques, you have significant advantages that are summarized in this picture. Okay? This is what we saw up to now. Okay, today, first message, we need to rank the documents, and so we have to understand why we need to rank the documents. But please keep in mind that the web search engine that you use daily, I guess Google, already provides you a ranking among the documents. So it is, I would say, pretty clear that actually this technique is used in commercial system. And we saw that we can do this kind of ranking in a number of ways. Two options are term frequency and tf-idf, we will see later on. But now that we have the techniques to define a ranking, we need also a new mechanism to represent documents and query, and this new mechanism is based on the concept of vectors. So each document and each query is represented as a vector. Good, let's start. Why do we need a ranked retrieval? As I said to you before, in the Boolean retrieval, basically either a document match or does not match a given query. So either you get it in the results or not, but there is no ranking among the results of a given query. Okay, we discussed in several examples that Boolean retrieval works pretty well for experts. If you know how to make a good query, you can select very precisely the documents in your collection set. In principle, clearly, you can have applications that handle the queries. They do not have problems in a huge result set of documents. But this is clearly a big problem for standard users, right? I mean, imagine that when you do a query, you get back, I don't know, 1,000 of results. Because again, in the Boolean model, we do not have the concept of ranking. If you have 1,000 of results, it's almost impossible to select the ones that are more relevant for you, right? Unless you can dig into the query and reduce the size of the result set. But again, this requires usually some expertise. So the question is to what extent we can design a system that is more, I would say, friendly for common users. Okay? Again, Google is used by experts. You are probably good candidate for being expert in the future or even now, but is not a good candidate for, Google with the Boolean retrieval model will not work for my mother, as an example. Okay, good. So, furthermore, the Boolean query, unless you do not know exactly how to optimize the query, can give either too much or too few results. As an example, here you have two very similar queries. And the query are standard user d-link 650. Okay, and you see you get back on a given collection 200,000 hits. As soon as you add into the query card and found, notice that we are talking a Boolean conjunction. Okay, so you have and among the terms. Immediately you get 0 hits. Okay, so this is clearly a problem for if you do not have the proper skill in order to define the proper query. Okay? If you assume that you can rank the documents, clearly this is not anymore an issue because you can show up for each given query the top, 10 results. This is actually what happened with Google. Okay? And thus the user can possibly walk through all the possible documents, page after page, looking first for the highest ranking documents and then for the other ones. Okay, the algorithm works is clearly more relevant results are ranked higher than less relevant ones. Okay, this is the basic assumption, and so our goal is to design a system that can properly implement this observation. Just to give you an example about Google, what are the click probabilities for the ranking position? And as you see, about 60% of the clicks are on the first in rank, and then there is immediately a very significant decrease in the probability. And roughly, either a document gets clicked because it's in the first page, or basically is not clicked at all. Okay, that's the probability distribution. Okay, so let's keep in mind this goal. So more relevant results are ranked higher than less relevant results. And let's design a system that allows us to implement this. Okay? Okay, so how can we accomplish this ranking? Assuming that, as an example, we can assign a score to the query document pair. A score this is between 0 and 1. Okay, 1 means that actually that query perfectly matches the document, and 0 it means that the query and the document are not correlated at all. Okay, so basically this score allows you to measure to what extent the document is relevant for a given query. Okay, how can we implement this score? So assume that now at the beginning that we have one term per query, and clearly if the term does not appear in the query, the rank is 0. If the term appears in the query, the rank is 1. Or even better, the more the term appears in the query, the highest is the rank, up to 1. Okay, this is the most simple, say, idea. And actually, we will see how to implement this idea in a number of alternatives. Okay, does it make sense to everybody? Okay, good. So, assuming that a document and the query can be seen as two sets, one possibility is to measure the overlap between the two sets by the Jaccard coefficient. Okay? So one possibility, and the Jaccard coefficient is defined as follows. Basically, you have the query and the document. You have the intersection over the union. Okay? So if the query and the document are the same, clearly you get 1. Okay? If they have nothing in common, so the intersection is null, you have 0, and then you have values between 0 and 1 representing all the other possibilities. Okay, what is good, what we like about the Jaccard coefficient is that actually consistent with our idea of defining a matrix, providing us a number between 0 and 1. It works. Okay, so as an example, if we have this query and this document, the query is Edith of March, and document is Cesar died in March, so the Jaccard coefficient is the intersection, and the intersection is 1 because we have only March in the intersection, over 6 that are the different terms between those two sets. Okay? Good. Do you see any possible problem? Just to give you an hint related to the fact that we are looking at two documents as sets.
That we are not taking into account the possible multiple occurrences of the same term.
Exactly. The main problem you can envision in this, in the use of the Jaccard coefficient is that we do not take into consideration the frequency of terms in a document. Let's make an example. If the word or the term soccer is a lot of time in a document, most likely it means that that document is related to some extent to the soccer. Okay? And similarly for other documents. So indeed, the main problem we have with the Jaccard coefficient is that it does not take into consideration the term frequency. We are considering we are not considering the term frequency. And even more importantly, in general, I would say that rare terms are more informative than frequent ones. This is the idea why we removed the stop words up to now, right? Stop words are very common. You might find it in any document, and so the contribution in terms of information is relatively small with respect to very specific terms. Okay, so we need somehow to understand, to take into consideration this concept of rarity. And so we need something that is a bit more sophisticated to normalize the document. Okay? To take into consideration all these aspects. Okay. So let's start with the, so basically we have, I remind you, we have two main observations now. A, if we use Jaccard coefficient, we do not take into consideration the frequency of a term. So our first goal is to introduce something which allows us to take into consideration the frequency of a term. B, we have another observation, another key concept. Rare terms are likely more informative than frequent ones. So first of all, let's deal with the first observation, and let's take into consideration the term frequency. Okay, this is the idea. So I remind you that in our original model, the Boolean one, we didn't consider the frequency, at least in the basic, say, scenario. And simply we had the 1 or a 0, 1 if the term is indeed in the document, a 0 if the term is not in the document. Frequencies are not considered. Why? We want to move to a situation like this one, in which we have a term document count matrix, in which for each document, not only a number different from 0 means that that term is in the document, belongs to the document, but also tells us the frequency, the occurrences. Namely, we are to some extent answering to the main observation, to the first observation we made before. So this means that, I don't know, in Antony and Cleopatra, Antony appears 157 times, Brutus 4, Caesar 232, and so on and so forth. Okay? This is the frequency of a term in a given document. Okay. Notice, however, that in this model, so basically, what is the model now? The document Antony and Cleopatra is defined by a vector of terms in which, for each term, we have the frequency of that term in that document. Okay? So this is the so-called bag of words model. Notice that we do not consider the order of the terms. So two documents containing exactly the same terms, but in a different order, are basically the same document for us. Okay? So this is an example. If you have John is quicker than Mary and Mary is quicker than John, are represented in the same way in the bag of words model. Okay? To some extent, we are going back, because remind that we use positional indexes in order to distinguish among those two documents, right? But okay, we will see that despite this, say, step backwards, anyway, this model is very powerful, and this is the premise for an even more advanced model. Okay? So is the bag of words model clear? I take a document, I take the frequency of the terms in the document, and I simply list the terms with their frequencies. This column, okay? This is the bag of words because we do not take into consideration the order in which terms appear. Okay. So in this case, clearly we have this concept of term frequency. And the term frequency is the number of times a term T occurs in a document D. And so the question we want to answer is, the original question we want to answer is we want to use such information in order to define a score to a query document pair. Do you remember what is the main purpose today? Rank, okay? In order to rank, we need a score. We need a number that tells us what is the position of that document with respect to a given query. So we need a score to the query document pair, which allow us to rank the documents with respect to a given query. And so TF, the term frequency, is a possible candidate, okay? Now, we could use raw terms. Namely, we could say, again, that if a term occurs 10 times, it is in a document, and in another document appears only one time, so this document is 10 times more relevant than this one. But clearly, this is not true, right? Usually, you cannot assume that there is a linear relationship between the frequency of a term and the relevance of the term in the document. So it's true that there is a connection, but it's likely not linear, and indeed, the proposal is to assign a weight that is logarithmic with respect to the frequency. Okay? So, is the term appeared in the document, we have a value. If it doesn't, the weight is 0. Okay, and this value is proportional to the logarithm of the occurrences of the term in the document. Okay? Is it clear the reason? Because otherwise the relationship would be linear, and it's not actually true that as much times the same term appeared in a document as relevant is that term in the document. It's clearly true that there is a relationship, but it's not linear, and so we assume it is logarithmic. Okay? Good, so now we have all the ingredients. Why logarithmic? Because you see, if the document does not contain the term, the weight is 0. If the term is present only 1, you have this normalization 1 plus, which allows you to tell that it is 1. If it's 2, is 1.3, but you see, if it appears 1,000 times, you do not have a relevance that is 1,000 times higher, but it's only 4 times. Okay? This is the idea. Okay, now that we have discussed this idea of logarithmic weight, the score is pretty simple. The score of a document related to a given query is the sum of the term frequency of all the terms that appears both in the query and in the document. It is not a linear weight, it is a logarithmic for the arguments we discussed so far. Okay? And clearly, the score is 0 if the term is not present in the document. Questions? Okay. let's go forward, and if we will have time at the end of the class, we'll do the exercise. That anyway, please do it at home, okay? Good, so do you remind the two observations why Jaccard coefficient was not okay? One was that it does not take into consideration the term frequency, and the other one was that rare terms are likely more informative than frequent terms. Okay? So we need to plug this second observation into our scoring system. Good. So, not only we want to measure the frequency of a term into a document, but in order to measure, to have a proxy to the measure of the rarity of the given term, the rarity is with respect to what? The rarity is with respect to the collection. So the rarity is to what extent a given term is rare into the collection. Why? What is the intuition here? Assume that a term exists, is present in only one document. What is the idea? Is that immediately you can select that document if you provide an input that term. Okay, so here the rarity is extremely informative because it's the only document actually having that term in the whole collection. Okay? So what we want to measure now is a measure of the rarity of and thus the frequency of a term into the whole collection. As an example, okay, the assumption is always the same. Rare terms are more informative than frequent ones. But let's assume that you have a term with, as an example in the collection, you have this arachnocentric. You know, arachnocentric, I don't know, maybe I use this word in English. Okay, I'm not so good in English, but maybe I use this word in English only during those classes. I never use it in other contexts. So it is clear that if you identify a document with this given term, you can identify it very precisely. And so basically, we want I weights for rare terms, which allows you to discriminate in a very precise way among the documents, simply because they are rare. Okay? Good. Okay. Now, again, this is the same observation we made before. We would like to have a scoring system now taking also into consideration. We don't forget the term frequency. Indeed, if you remind this, the title of this section is TF, term frequency, IDF. We have still to understand what is the meaning of IDF, but this IDF part takes into consideration the rarity of the term. Okay, and so we would like the rare terms will get the highest score, while frequent terms will get a lower score in terms of clearly the power of discriminating among the documents, even if we want they have positive weights. Okay. Okay, so recap: high weights for rare terms, low positive weights for frequent terms. Okay, we will anyway use the document frequency, but we will also consider the frequency of a given terms in the whole collection in order to identify the rarity of the terms in the collection. Okay, and this is the concept of IDF. Okay. So the F is the documents frequency, namely are the documents we are counting in the collection, the documents in which the term T appears. Okay, so just to make an example, if arachnocentric or whatever it is appears in only one document, is 1, the number of documents in which it appears, okay? If it appears 10 times, it's 10, and so on and so forth, okay? Now, the IDF weight is again a logarithmic of what? Of the inverse of this frequency. Because as much the term is rare, as bigger we want the contribution of in the scoring, okay? Okay, so this is why we have the inverse. And clearly this IDF, which stands indeed for inverse document frequency of the term T, it's a measure, since we want a measure of the informativeness, it's inverse proportional to the frequency, that is the rarity. As much a term is rare, as big is informativeness, and thus as big is the IDF. Okay? So we have noticed that we have noted that we have this logarithmic both in TF, in the term frequency, and in the IDF. So just to have a picture of the value of the tf-idf, of the combination of the two, if you have very frequent words, you have anyway a positive value, but a big one. If you have very rare terms, rare words, that provides you a lot of information, are very informative, you get a high tf-idf. Okay, it's a combination between the two. Taking into consideration both the frequency of a term in what? In a document, and the inverse document frequency of a term in the collection. Okay? We are putting together those two pieces. Okay, so those are examples of the document frequency. And as you see, as bigger is the document frequency, as smaller is the IDF. As more rare is the term, so as more rare is the document frequency, as bigger is the IDF. Okay. Now, just for fun, you see there are examples here you have the reference. I like this. This is as an example the highest tf-idf words in classic physics tests. And this indeed tells you that if there is relativity, very likely is a document by Einstein. Okay, because likely the others didn't use the word relatively so much. Bulb is by Tesla, and again we can expect that is by Tesla. Huygens is refraction, and again we can expect is refraction. Water is by Galileo. Maybe this is a bit more surprising, right? Because I don't know, at least to me, to my knowledge of Galileo works. But again, now the concept, the nice idea is that you can build tf-idf on a collection, and in this case the collection is the collection of classic physics tests. Okay. Notice that IDF affects the ranking of documents that have at least 2 terms, right? Because what is the contribution of the IDF? It allows you, if you have 2 terms, it allows you to increase the weight of the term that is most rare in more rare in the collection, and thus more informative. Okay, this is the idea. It increases the contribution of this term. Okay, so if you have, again, arachnocentric line, what does the IDF weighting? It increases the relative weight of arachnocentric, which is pretty rare, with respect to the relative weight of line, which is more common. And the score, as you can expect, is the sum up of all the term in the query, sorry, the sum up of all the tf-idf of the term in the given query. The score between the query and the documents. Don't forget that our main purpose is to rank documents according to a given query. And so the first technique we used is based on term frequency. Okay, the first one was based on Jaccard, then on term frequency, and now we introduce those IDF. Okay? Good. Now this is an example which tells us that, okay, we had basically two options to consider the rarity of a given term. Either to consider the collection frequency or the document frequency, namely to what extent a term is rare with respect to a given collection or to a given term. And clearly, you see that this discriminative power of the document frequency is higher. That's why we consider this in our not only in our system, in all the systems. Okay. So now we have all the ingredients. We can put together all the terms and the weight that we will consider in order to define our final ranking among the documents is what? Takes into consideration the term, the frequency, and the inverse document frequencies. This is why we call it TF weight, this part here, and IDF weight, this part here. Okay? This is indeed the, probably the best known and actually one among the most used weighting scheme in information retrieval. Okay, so what we want to do is we want to assign a tf-idf weight for each term in each document D according to this weight. And the idea is that this weight will increase with the number of occurrences. This is the term frequency. But will also increase with the rarity of the term in the collection. And this is the IDF contribution. Questions?
Can you repeat what is a DFT?
The document frequency of a given term. In how many documents in the collection that term appears.
So it is always less than n?
Yes. Yes. A document, okay, what happens there? If a document appears in all the, a term appears in all the document, DFT is?
EDFT.
No. If a term appears in all the documents in the collection, is n. So n over n is 1, log is 0, and so the weight is 0. Indeed, since that term is in all the documents, it doesn't provide you any kind of information, right? All the documents with respect to that term are relevant.
In the last slide, why you mentioned there are at least 2 terms in the parent? In the last
This one?
The first sentence, why the previous with at least 2 terms?
Because basically, if you have a single term, okay, you have a different weight, but actually that weight is only with respect to that term and to the whole collection. While if you have more than one term, so you want to see what is the contribution of each term in the query. Indeed, is a little effect, which does not mean that it does not have effect, but as a little effect because anyway, if you have only a single term, all the documents are ranked according to that single term. While if you have more terms, the contribution of all the terms depends on their frequency. Okay? Other questions? Okay, good. Okay, so now we know why we need ranked retrieval. Yes?
Just a practical question. But since the score depend from the query, how these ranks are computed at runtime. So when the user makes the query, then so how they are.
You see that the weight depends on the terms and on the documents. Then the score depends on the query. Okay.
Okay. So if the score depends on the query, so how can I assign a score to a given document just when I have the query? So
because you have the weight, here the weight, you have only terms and documents in this weight. Then when you want to compute the score, namely a ranking, you have to apply, okay? This is important, okay? Here you have only the weight of a given document is term and document. When you apply the query, the score is a function of the query and the document. It's, okay, the score now is a matter of query and document. Other questions? Okay, now, so we need ranked retrieval because, Boolean queries are pretty effective if you are an expert. You need some skills in order to distill the right query, and possibly is an iterative process through which you dig inside the knowledge, the knowledge of your collection. But anyway, you need to be an expert. Okay. Furthermore, in general, the number of documents that are given as answer to a given query can be pretty big, and thus it's difficult to be actually understood for common users. So we need a system in order to rank the documents provided as answer to a given query. So now, how can we rank? Hypothesis A, Jaccard. We say, good, but it doesn't work because it doesn't consider the frequency of a term and the rarity, which is proportional to the capacity of giving information by a given term. So we introduce TF to take into consideration the frequency, and IDF to take into consideration the fact that rare terms are more informative. Okay, this is the whole picture. Now, we have to move towards the vector space model. Okay, again, this is the original matrix behind the Boolean model. Now, this matrix has been modified with this matrix that takes into consideration the frequency, the occurrences of the terms in a given document. But now we will have a weighted matrix in which for each term we will have a weight, and this weight we now know is the tf-idf. Okay? So, is the W of T and D, where T is the term, and D is the document. clearly, in order to, while in order to compute the TF, we simply need the term and the document. In order to compute the IDF, we need the term and the collection of documents. Okay? Good. Okay, so now each document is represented as a vector in this v-dimensional space of real number. Okay? This is the vector of Antony and Cleopatra. This is the vector of Julius Caesar. This is the vector of the Tempest, and so on and so forth. Those are the vector with the tf-idf value for each of the terms. Okay? So we have a v-dimensional real value vector space. The terms are the axis of this space, and documents can be seen as vectors. Okay, let's make a very simple example. Assuming now, just for the sake of simplicity, that we are in a b-dimensional space. Okay, we are in a b-dimensional space, which the Antony and Brutus terms. Antony and Cleopatra will be something with 5, 1, 2, 3, 4, 5, 25, so it's here, and 1, 21. So this is Antony and Cleopatra. I'm just considering the space with the two vectors Antony and Brutus that are the axis of our space, okay? So Julius Caesar is 3, so 1, 2, 3, and 6. So this is Julius Caesar. In this particular case, the Tempest is here. And so basically, those are the vectors, right? Representing the documents. Now we are looking at, for the sake of simplicity, even because it's the only way we can represent it, we are looking to a two-dimensional space. Maybe we can handle a three-dimensional space. But please consider that in the reality, this is a huge space made of thousands of terms, okay? And also consider that each vector is very sparse, because clearly the vector space is made of the terms in the whole collection. But each document will contain only a limited number of terms in the whole collection. Okay. Does this picture and this observation make sense? Okay, so guess. Those are documents. Our query will be again another vector in the same vector space, right? And thus, the next question is, how can we understand whether two vectors, the vector query and the vector document, what is the distance between those two vectors? And we have to explore a number of possibilities, basically two, but the idea should be now clear, right? If you understand and accept that a document can be represented as a vector, a query is usually a subset of the terms in a document and thus can be represented as well in the same space. And thus the next question is you have two vectors and you want to see to what extent the vector query is relevant for the vector document. A natural answer is as less is the distance, as better is the document for the given query. Should make sense, right? Okay. So indeed, the key idea is that not only we represent documents as vector, but also we represent query as vector. And now, what we can do is we can rank the documents according to the proximity. So going back to your question, we can represent the documents according to the proximity to the query. That's the whole idea. Okay? Document, query, this is the distance. Document, query, this is the distance. This document is more relevant because it's closer with respect to this document. Okay, so the proximity basically is a similarity. Okay? Good. Now, we have this concept, we have this idea of proximity as a similarity, as a proximity as a tool in order to attribute a score between the documents with respect to a given query. And now we need to explore what are the alternatives to implement this solution. Okay? Okay. Okay, the first, maybe the most straightforward solution came to our mind is the Euclidean distance. Okay. Euclidean distance is not a good idea. Can you... Now, let's go back to this picture. Okay. This is a document. Okay, and it contains the term Anthony and Brutus. Okay, if I consider this document, maybe it contains twice the term Anthony and twice the term Brutus. This is 1, this is 2, this is 1, this is 2. Now, if I consider the Euclidean distance, this is the distance, right? This one. Which can be arbitrarily big. If instead of twice is n time such big. But at the same time, the informative content of those two documents is basically the same. They contain only two terms in the same proportion. There is a difference. Are two distinct documents, true, but at the same time, the informative content is the same. Okay? So we need something different. Euclidean distance doesn't work. Does this make sense? It doesn't work because basically the documents that contain exactly the same terms in the same proportion, not even a different proportion, can have an arbitrarily big Euclidean distance. As large as you want, as big as you want. And this does not work. So we need something different. Since we are talking about vectors, if it's not the Euclidean distance, it's the distance between what? Between angles, right? And indeed, if you see this picture, the two documents we discussed so far, that basically have the same information content, the angle is 0. Okay? So a good candidate is indeed using the angle, a measure of the angle, of the difference in terms of angle, and indeed the standard, would say, measure for the similarity between documents is the so-called Cosie Similarity. Okay? So basically, if the angle is 0, the Cosie similarity is 1. If the angle is anything else, it's at most 1, at least 0. So you have a number again, as we wish, between 0 and 1. Okay? Orthogonal documents have a distance 0, while those documents are orthogonal in the sense that there is no correlation between the terms. Parallel documents have distance 1 for the argument we saw up to now. Is this clear to everybody? Questions? Yes?
Parallel couldn't even mean that they...
Okay,
I mean, if they're not
No, okay, they have parallel, it means they have the same origin, yes, okay. Okay, we can represent, remind that we can represent now if we want, and then we'll discuss it. Basically, we can represent all the possible documents as vector starting from the origin and with a given length and a given angle with respect to the origin, okay? Which is defined by the contribution of each term to that document. Okay? Good. Okay, this is a picture in which basically you can represent all the documents with respect to two terms, rich and poor. Okay, here you have the query, which is rich and poor, and thus it's basically at 45 degrees in this particular picture. And so you can see what is the distance between two documents simply computing the angle or the Cosie similarity. Okay? So the idea is that we want to rank the documents according to this angle. Because basically we have in mind this observation that is the picture we saw before. Okay? If you take a document and append it to itself, are you adding something in terms of content? You take any document and you append itself, you are not adding anything, exactly the same terms. In this particular case, even if we do not consider in the bag of words, these are exactly in the same order. Okay, so there is not even if we would have a more sophisticated model, there is no contribution. Basically, it's the same contribution in terms of content, right? But at the same time, if you consider the Euclidean distance, there is a distance. While if you consider the angle distance, there is no distance. And that's why we want to take into consideration the angle. Okay? Okay, so basically, since measuring the angle or measuring the cosine between the query and the document are the same thing, so those are basically equivalent. And furthermore, what is interesting is that, okay, you know the cosine, right? Is a monotonically decreasing function of the angle. So this is the angle. If it is the same documents, the cosine is 1. So query and documents, angle 0, it means that the query perfectly matches. If they are orthogonal, there is no relationship, and so on and so forth. You have all the intermediate possibilities. Okay. Okay, in order to compute the cosine, we need first a normalization step. So basically, what we do, we normalize the length simply dividing each component of the document by the length. So it's the L2 norm. And thus, after normalization, the length of each of all the documents in our collection will be 1. Notice that we are changing the length, but not the angle, right? Which is the information, what we discussed to be the main information we need in order to implement our ranking system. Okay? So we are normalizing, and so we have, after normalization, we have unity vectors. Okay? So by these unity vectors, that basically you want to measure the similarity between Q and D, the query vector and the document vector. This similarity we discussed that is actually the cosine between the two vectors. This cosine can be measured normalizing the vectors. That's why I consider the vector q divided by the module of q. We are normalizing. We consider the vector d divided by the module, and so we are normalizing. And finally, we'll get the cosine. Okay. Now, in our don't forget that we started from the fact that both q and d is a weighted representation of term in the query and in the document. In particular, we discussed that the most suitable and the most effective and the most used representation is tf-idf. But it is not the only one. Okay? So basically, don't forget that we started from here. Each document, entity and collaborator, is a vector of what? Of tf-idf. Vector of tf-idf. Now we'll take a query, we translate it into a vector, and basically we compute the Cosie similarity. Okay, so qi is the tf-idf weight of the term in the query. Di is the tf-idf of the term in the document. And then we calculate the Cosie similarity. Okay. Yes.
What's V?
V is the dimension of the vector space, namely the number of terms. The number of terms in our collection. Okay? Okay, so basically if you have normalized vector, since the module is 1, you can compute it in such way, very, very, very effective. Okay, because basically what you have is that you are projecting all the vectors, irrespectively from the length, into the unit sphere. You are normalizing, and so now the length is 1. Okay, so it's a unit vector. And what you are calculating is the Cosie similarity, namely the angle between the query and the given document. Questions? There are no questions because there are problems, or no question because everything is clear? Okay, good. So now let's consider an example. Okay? So we want to measure how similar are those novels. Sense and Sensibility, Pride and Prejudice, and Wuthering Heights. Notice that the first two are by Jane Austen, and the third one is by Emily Bronte. Okay? We need this information for a question we'll have later on. Okay? Okay, what you do is basically you consider the term, in this case affection, jealous, gossip, and wuthering, and you measure the the frequency in all those novels. Okay? What is in this particular case, in your opinion, the most rare term, the one that will have the highest tf-idf? Huh? Gossip. Let's see, gossip appears in two documents.
Wuthering.
Okay. Well, since wuthering appears only here, if wuthering is in the query, you do not have other options that go to Wuthering Heights. So in terms of IDF, wuthering is actually the ones with the highest IDF. Okay, just to recap what we say. Okay, so what you do now is that you have the term frequency. We discussed why are we applying this? Can you remember me? Can you please tell me? Why are we normalizing by log?
To not let frequency become too discriminated.
Right. Yes, it's true that the term frequency is important, but it's not linear, the relationship. We want to smooth this relationship, and thus we apply the logarithmic, and so from here we go there. Okay. Okay, now actually we are not doing IDF weighting for the sake of simplicity. Okay, and finally, from the log frequency weighting, what we do is we normalize, we do the cosine normalization, and thus, if we want to measure the distance, namely the similarity between two documents, we use the cosine, and the cosine is pretty simple. We say that since we have normalized, we simply sum up and multiply term by term. And so we have 0.78 multiplied by 0.82, and so those are the two vectors, and I multiply term by terms, and I get that SIS-PAP is 0.94, 0.79, and 0.69. Okay? Okay, now, clearly, good. Makes sense. Why? Okay, it makes sense because of the mathematics. Good. And clearly, this is a good answer, actually. We built this model, this system, in order to make it working, and indeed, we have an answer. But do you see something interesting here? Namely, let's consider this question.
The same author is more likely to use the same words.
Right. Okay? The same author, Jane Austen, more likely will use the same dictionary, the same terms in her novels. While two authors most likely will use different. And that's a kind of confirmation of this observation. Okay? Okay, good. So, okay, computing the cosine score, it's relatively simple, as we say before. Now, consider that, okay, we actually have in mind now, okay, we made all the steps, and so we have in mind that we, for each, for term frequency, for document frequency, and for normalization, we would like to use the logarithmic term frequency, the logarithmic IDF, and then the cosine normalization. This is what we explored so far, and thus this is the, say, a straightforward, a natural solution for us. But actually you can combine all those possibilities, okay? And we will see later on that actually one among the most used techniques is not so natural, according to what we said before. It appears not to be so natural, but let's see. Okay, so basically we can apply different weightings for queries and documents. And so you have this notation in which you have 3 terms for the query, for the documents, sorry, DDD, and 3 terms for the query. 3 terms from what? 3 terms defining the way in which you deal with the term, the document, and the normalization. So let's see this example. The LNC for the document. The L stands for logarithmic non-cosine. This is what we do for the document. And now what is strange for us is that we are not applying IDF to the document. And this is a bit strange with respect to what we said before, right? While for the, for the query, we have LTN, where LTN stands for, again, logarithmic, IDF, none. Okay? So we are not normalizing the query in this particular case. Okay, so you can combine all the possibilities between query and document. Now, this LNC.LTN, namely for the document logarithmic TF, no DF weighting and Cosie normalization, and for the query logarithmic TF, IDF and no normalization is a kind of standard, one of the standard options. And so the question is, why are not we going to do IDF weighting weight in the document? And now the answer is the fact that remind that actually we are interested in a scoring between query and document. If you apply IDF to the query, to some extent you are considering already the IDF contribution, namely the rarity of the term in the query with respect to the collection in the query. And so you don't need it in the document, or is less fundamental. I'm not saying you don't need, but it's less crucial to consider it also in the way in which you treat the document. Okay? And furthermore, there is so this is a matter of effectiveness, and there is also a matter of efficiency. Clearly, it's not clear actually. But if you do not apply the IDF to the documents, it's easier to apply optimization technique like the compression. So that's why, in some cases, this LNC-LTN works pretty well anyway. Okay? So now let's consider an example. The example is the following. The query is best car insurance, and the document is car insurer auto insurance. Okay, so let's see what happened. So you have the query. First of all, you can consider the term frequency. And so clearly you have a one only in those terms that actually appears in the document. Then you can see the query document frequency, namely how many terms in the query appears in the document, in the collection. This is the IDF. And finally, you get the weight. Okay? Remember that we are considering LNC LTN. So for what concerns the query, we are logarithmic IDF non-normalization. While for the document, we don't have IDF because we are in the case in which we are not considering IDF. Again, you can see this is the raw version, this is the normalized, the weighted ones in which we apply the logarithmic, and finally we have the weight and the normalized version. Okay, have a look to this example. I think it's pretty straightforward, sorry. So there should not be a question. What is important is that you remind that not necessarily in practical system you have to apply the same steps to the document and to the query. You have different combination in terms of counting the terms, in terms of considering the rarity, and in terms of normalizing. Okay? Keep in mind this table. Questions? Okay. We have other 5 minutes. I want to show you 10 minutes. Oops. Vabbè, un secondo. Okay. At that link, okay, now it's not clear, but I'll share clearly the link. There is a very nice IPython notebook, Jupyter notebook to experiment with this stuff. Okay. We saw last time, very quickly, don't worry because we are going to have a lab further on in which we'll recap everything, we'll do some exercise. Now I just would like to give you at least the pointers to start playing with this stuff. So we already saw NLTK, and we saw how to basically run the main functionalities like stemming, like stop words, like tokens, both for words and for phrases. Okay, and so we build a very raw inverted index starting from this tool. Today I just would like to show you this other tool, which is pretty nice. It's named sklearn. Okay, and this tool will help us in doing some experiments with this vector space. It's more convenient for this vector space, but also in the future will allow us to do some experiment with the classification of the documents. Because you can expect that, now think about it. If documents are points in a high-dimensional vector space, one natural question would be how to cluster such documents in order to assign a category to each document. So the question is, to what extent is true that all documents of a given categories are actually close by, are represented by points that are close by? And so we need to apply some clustering algorithms, we will see later on, which help us in performing such task. Okay? This is one of the purposes. But now, for now on, we will experiment with sklearn for looking at some of the things we discussed so far. Now, we have a very basic collection. The collection is made of 3 documents, which are those 3 phrases. The count vectorizer is the main object which allows you to experiment with the tools we saw for natural language processing. Notice that it doesn't provide, as an example, stemming. So if you want to use stemming, you used to apply stemming by NLTK. It's not given for free by the count vectorizer, but it provides you stop words. You can use the analyzer with words or with sequences of characters. Okay? Now that's interesting because this is the concept of n-gram we saw in the last classes. So you can have b-gram, 3-gram, and stuff like that. Those are filters to consider into the output of this class documents with a given document frequency. Okay. And now it's very, okay, 1 second, it's very simple. If you run it, you'll get this feature set. Okay. Let's see as an example if we don't consider the stop words. Okay. If we don't consider the stop words, simply here we place stop words none. Now if we run the same algorithm, you see that the number of features, what are the features in this case? The number of terms are increasing significantly because now you have all the stop words we saw before. Okay? So now, this is, those are the features now, and this is the representation of the documents in terms of the matrix we saw so far with the frequencies of each word into a given document. So the word number 0, 1, 2, 3, 4, 5, 6, 7, which is 0, 1, 2, 3, 4, 5, 6, 7, time appears twice in the first document. Let's see whether it's true. You have indeed time and time. Okay? So this is actually the same matrix we saw today with the term frequency. You can build the vocabulary in which the vocabulary clearly contains the feature we saw before and also an ID for the vocabulary. You have again this concept of n-grams, which allows you to explore not only single terms, but also in this case b-grams, because n is equal to 2 or 3 grams or whatever you want. So what I would like to stress is that all the concept we saw up to now on our slides can be actually implemented with this device, with this library. Okay, as I told you, this is not particularly interesting for us. This is a way to filter out terms that are very rare with mean document frequency and max document frequency. What is interesting for us is the tf-idf vectorizer. Okay. So basically now what you have is that tf-idf vectorizer, which allows you to get the tf-idf representation of those terms. And again, you have the vocabulary, which is made of the terms in the sentence. This is again made of 1, 2, 3 documents. And finally, where is it? Okay. This is the representation of all the terms and the weight that you can assign accordingly to what we have seen in our slides. So now it's I will give you the links, and it's more an invitation to play with this kind of tools, because actually if you play with those tools, most likely you understand the concept behind the tools. And anyway, an exercise lab is programmed further on during this class. Okay? Good. It's everything for today. See you next time. Okay? If you don't have questions, do you have questions? Okay, thank you.